So if we look at our second example here, this says a friction and massless pulley is suspended from the ceiling. A light string passes over the pulley and one end of the string is attached to a mass of 2 kilograms and the other is attached to a mass of 4 kilograms. So M1 equals 2 kilograms, M2 is equal to 4 kilograms. What is the acceleration of the system when the masses are released? What's the tension in the string? Now, first thing that we always do regardless of the problem is we'll sketch our free body diagrams just to make sure there's nothing tricky. So FT will pull up, FG1 will pull down, and this will be on mass 1. Mass 2, FG2 will pull down, FT will pull up. And this will be for mass 2. And I'm drawing these a little sloppy. Let me do that cleaner because we can make some estimations here. So we expect the whole object system to go to the right, correct? Because 4 is heavier than 2, so it should slide over. So that means that FG2 should be bigger than FT in order for it to accelerate downwards. And FG1 should be less than FT in order for the left side to accelerate upwards. Now, you could do what we did before and have sum of F1 equals M1A1, sum of F2 equals M2A2. That's totally fine. It works. It's great. You can do that, work through it. But I'm going to show you kind of a trick that we're going to do. So I'm going to imagine around this pulley, like I'm basically going to imagine stretching this string straight. So as opposed to being bent, imagining it straight. And I'm going to say if it moves towards the M1, that will be a negative motion. If it moves towards the M2, that'll be a positive motion. So if it goes up and over like that, that would be positive motion. If it goes up and over to the other direction, that would be negative motion. And I'm going to pretend like it's all happening in a straight line. This works because we're assuming that the string is light and that the pulley is massless and frictionless, that we can pretend that it's all in a straight line. So what would that be if we imagined straightening that out? It would look something like this. And we'd have FG2 pulling to the right and FG1 pulling to the left. Right? Because if you imagine, straightening that string out, so we're not actually physically moving it, we're just imagining it in our brain, kind of twisting our axes. This is a little weird. If you have questions about it, ask me in class and we'll talk through it. It's just a way that we can kind of rework this because of properties of math. So what this means is now we can treat this as a single system, basically one big object of M1 plus M2 that's being pulled to one side with FG1, being pulled to the other side with FG2. So imagine this is one big solid object. That means the sum of the forces would equal to FG2 minus FG1. And that will equal MA. Well, what's M? It's the total mass, M1 plus M2, because it's the mass of the entire system, times the acceleration of the system. So A right there. So that gives us that M2G minus M1G equals M1 plus M2 times A. That means our A equals to G times M2 minus M1 over M1 plus M2. A equals 4 minus 2 divided by 6, so it's 1/3 G, which is going to be approximately 3.33 meters per second squared, because it's roughly 1/3 of 10. So that gives us our A, and you'll notice I only had to solve one equation. I didn't have to solve a system. Again, system would totally work, but we can save some time here. We will have to do a system of equations to find FT though, because for, say, mass 1, the net force is Ft minus m1g, and that's going to equal m1 times a. So Ft equals m1 times a plus g. So Ft is going to equal m1 times 4/3 g, and that's going to be what? I'm not sure. 2 times 4 is 8 divided by 3. 8 times 3 1/3, so we're looking at 20 something, maybe 25-ish, if I'm doing that quickly in my head right. But you can go through and calculate that yourself. So you notice we did need to introduce a second equation for Ft, but that was just looking at one of them rather than both. So this is a second example of the kinds of problems that we can solve with dynamics involving Atwood's machines.